Okay, so in a previous video, you have learned about pressure and what pressure is, this idea of a force per area. And in this video, we're going to look at how pressure changes in a fluid. And this will be a static fluid, so we're in what we call hydrostatic, so the fluid's not moving. Things change when the fluids move, and you can look at the fluid dynamic video on that. There's two of them relating to fluid dynamics. But this is how does pressure change in a hydrostatic or stationary fluid. Now, we want to keep in mind that pressure in general, remember, because it'll help us frame this, is equal to our force per area. So let's imagine that we have a container filled with a fluid. All right. Now, if I take one tiny little area, let's say right here in this fluid, and I want to look at the pressure acting on that particular spot in the fluid. Well, what is causing the force on that spot? Well, it's the fluid above it. This column of fluid above that area is causing the force. And the area, of course, is this area that I designate. And so the pressure is related to the force of this column of fluid above it. And what force is that going to exert? Well, the weight of the fluid above it. So if I take the same amount of area and I look lower in my system, well, now this too is experiencing a force over that area, and it's this column of fluid that is exerting that force. I have more fluid above my location, and therefore more weight of that fluid, and one therefore has a higher pressure. All right, so as I go deeper, as I increase the depth, I increase the amount of fluid above my location, therefore I increase the force, and by increasing the force, I increase the pressure. And this actually is a linear change, which is kind of nice. So we can write an equation that tells us the pressure at any depth is equal to the pressure at the top. So if this is air, it's going to be our atmospheric pressure, and it's typically what we have, right? So air above, the pressure naught, so the pressure at the top, plus the density of the fluid times G, which is going to give us a connection to that weight and how far down that location is, where D is the depth. So this linear relationship tells us that as I increase depth, I increase pressure. Now, we also want to remember that Pascal's principle tells us that pressure at any given level in a fluid is the same. So pressure at a given level in the fluid is the same. And that is Pascal's principle. And this, in conjunction with the idea that pressure changes, is going to be useful as we examine problems where we're looking at pressure in a system where we have hydrostatics going on in that system. So Pascal's principle tells us that pressure at any given depth in a system is the same. And that pressure, any pressure, a change, is transmitted through the system equally. So this, in this system, would be the same, and it's also the pressure on the walls of that container. So pressure at a given depth is the same and is transmitted throughout the system at that same depth. All right, so let's use this idea of pressure with depth to solve a pretty basic problem, but just to practice it. So imagine that you have a submarine and it is cruising at a depth of 300 meters. And so here we have our sub, and it is cruising at a depth of 300 meters. It's in the ocean, of course. And what is the pressure that the sub experiences at this depth? Well, we are going to need to know the density of seawater And the density of seawater we are going to say is 1,030 kilograms per meters cubed. All right, so that's our density of seawater. Now, P naught is the atmospheric pressure, so the pressure of the air above the fluid. And this is 1 atmosphere at sea level, but we're going to operate in standard units, so we're going to use pascals. The pressure of air at sea level in pascals is 1.013 times 10 to the 5th pascal. So P naught is a constant, okay? It's a constant. The pressure does change at different points of the atmosphere. It's the same principle as this, but typically the problems that we're going to be looking at, unless given, if the pressure is given of air at any given altitude, then by all means you will use that pressure, but for the most part we're going to look at this as being the pressure of air at sea level. All right, and we're in the ocean, so it is at sea level. Okay, so let's use this equation. The pressure at the depth of 300 is equal to the pressure at sea level plus rho times g times the depth. So we have 1.013 times 10 to the 5th plus 1,030 times 9.8 times 300. And that is equal to 1.013 times 10 to the 5th plus 1,030 times 9.8 times 300. 3.13 times 10 to the 6th pascals. All right. So, just as a recap, as we go deeper, we know that the fluid above the location, the area that we're looking at, is going to contribute to the pressure at that area. That's this piece. This is the pressure of the fluid. And this piece is the pressure of the air above the fluid. And typically, we're going to look at that being 1 atmosphere or the pressure of air at sea level. All right. Good job.